Today we are going to discuss about Unit 4 Digital Modulation Scheme. The course outcome of Unit 4 is analyze the spectral characteristics and bit error rate performance of digital modulation techniques. So in the last class we have discussed about what is digital communication, what is passband transmission, and what are the different methods of representing the signal. Today we are going to discuss about frequency shift keying method. So what is frequency shift keying? Frequency shift keying, the frequency of the carrier signal is going to be modified according to the input signal, that is frequency shift keying. Here the name shift keying, which represents the input of the system, is going to be a digital signal, that is binary stream or data, or we can call it as symbols. So it is known as frequency shift keying. Then what are the two frequencies? Two frequency signals are used. One is to represent the high frequency signal and another one is going to represent the low frequency signal. So here we are considering only two bits, that is one for high frequency signal and another 0 for low frequency signal. The high frequency signal is represented as PH of t and the low frequency signal is represented as PL of t. This represents, PH of t represents the binary bit 1 and PL of t represents binary bit 0. If B of t is equal to 1, that is the information to the system is 1, the signal is going to be root 2 ps cos 2 pi f0 plus mo into t, or we can call it as sigma. Sigma represents the frequency change. 2 pi f0 plus sigma is nothing but the angular frequency change due to the binary bit 1. Similarly, B of t is equal to 0. For low frequency, the signal is equivalent to root 2 ps. So this root 2 ps is obtained from the average energy signal. So how to calculate the average energy signal? P is equal to V RMS divided by root to the whole square. So the maximum magnitude divided by root to the whole square by 2 is considered as the average root mean square value of the energy signal. So here we are finding out the magnitude. So that is equal to root 2 ps cos 2 pi f0 minus omega into t. So this is for high frequency and this is for low frequency. The only difference is there is a phase shift between 1 and 0. So here we are considering only the two frequency signals. Hence this system can be called as binary frequency shift keying. So let us consider this table. B of t is equal to, that is our input stream, D of t. D of t is nothing but the magnitude level or amplitude, maximum amplitude levels to represent this binary information. Due to unipolar coding, B of t is equal to 1 means only one level is allowed, that is plus 1 volt. If it is 0, then it is going to be minus 1, unipolar. PH of t, PL of t. So PH of t means high frequency signal. So for plus 1 volt from the origin to plus 1 volt, if the binary input signal is 1, then the high frequency signal is equivalent to plus 1 volt. For the same condition, the inverted signal is going to be, that is the low frequency signal, which gives you 0 volt. Then the next symbol is considered as 0. So if you are giving 0 as input, the distance from origin to the bit stream 0 is equivalent to minus 1 volt. So the high frequency signal for binary input 0 is going to be 0 volt. Then the low frequency signal is considered, so plus 1 volt for low frequency signal. So by considering all these conditions, the input signal 1 and 0, for this case the output signal S of t is going to be root 2 ps. From these two I can write root 2 ps cos 2 pi f0 is common minus and plus omega. So that is replaced as d of t, because that value is going to be either +1 or -1 for low frequency and high frequency signal. So when 1 is transmitted, carrier frequency is going to be f0 plus pi by 2 omega divided by 2 pi. So how we are obtaining this f0 plus omega by 2 pi? So this is equivalent to omega t. That is the angular frequency 2 pi f0 of t d of t into omega into t. So this is angular frequency omega t. So omega is equal to 2 pi f. So when we equate this, we will get omega is equal to f0 plus omega divided by 2 pi. Similarly, for input signal 0, carrier frequency is equal to f0 minus omega divided by 2 pi. So I can write the high frequency signal is equivalent to f0 plus pi by 2f, low frequency signal f0 minus omega divided by 2 pi. So as I told earlier, the binary input stream is considered as 0 and 1. So it is called as binary frequency shift keying. The same conditions are applied here. This is a block diagram for binary phase shift keying transmitter. So we are going to transmit the Bfsk signal from the source to the destination. So this is the block diagram. This block diagram consists of a source and a level shifter, inverter, and we have a multiplier, then one summer. So here the input sequence B of t is given to level shifter directly, and it is given to inverter. Say for example, if your B of t is going to be 1, in that case 1 is directly given to the level shifter. So the corresponding 1 bit is going to be converted as a unipolar equivalent voltage. So as I told you, if you are going to give 1, the unipolar voltage will be equivalent to plus 1 volt. So here we can see, so SH of t is equal to root 2 ps cos 2 pi f0 plus omega into t. So the same thing. Here we can obtain ps, tb, ph of t. Similarly, inverter. So for a one input bit stream, if you are giving that 1 to inverter, the inverter will inverts the level to 0. So at a time, this is going to be in on condition, this is going to be in off condition. Either one of the frequency signal can be transmitted. So for bit 1, it is going to be transmit the high frequency signal. At the same time, the low frequency signal is in off mode. Then if B of t is equal to 0, the condition is vice versa. Here it is going to be off condition and this is going to be on condition. This is the multiplier. So in this multiplier, we are going to multiply the unipolar output from the level shifter along with the high frequency carrier signal. So the carrier signal is considered as cos 2 pi fh of t. Similarly, here the low frequency signal, the same frequency, whereas the only changes here we have inverted the input signal. So 2 pi tp cos 2 pi flt, low frequency signal, carrier frequency. And this summer is used to add these two values. From that we can able to obtain binary frequency shift keying signal, so which is represented as S of t. So this is a mathematical expressions of the same. So S of t is a combination of pi 1 of t plus pi 2 of t. This leads to root 2 ps ph of t cos 2 pi fht plus root 2 ps pl of t cos 2 pi flt. Then this is the spectrum of binary phase shift keying signal. So here this is our reference voltage f0. This level is high frequency signal and this is low frequency signal. So bandwidth is nothing but the difference between higher cutoff frequency to the lower cutoff frequency. So this leads to 2b, and here from this point to this point, this is equivalent to 2b. So 2fb or omega b minus 2fb, so which leads to 4fb. So the bandwidth for binary phase shift keying is nothing but twice the bandwidth of Bpsk. So bandwidth of Bpsk is equivalent to 4fb. When we compare this bandwidth with Bpsk, twice the bandwidth. Okay. Then